Okay, while we're on the topic of logarithms, we want to throw one more idea in there, and that's what is a natural logarithm. So students will be able to determine values of natural logarithms, identify and apply properties, apply the logarithmic models, and graph natural logarithmic curves. So it sounds like a lot, but really you're going to see how related it is to stuff we already have done. Now, remember, we've done common logs, which were base 10. We've done logs, which were any base, but now we're going to make one exception to that rule. If we have a log that's base e, and you remember, when did we do base e stuff? And you got to remember pert and nert in order to answer that. So in the first part of the chapter, we were doing exponential growth continuously. So it naturally turned $1 into $2.72-ish cents, when we said if we could compound this as fast as possible, which they're going to say is sort of like a natural compounding. Well, natural logs, logs to base e. So right away we say, well, what's it look like? And we're going to have the same problem. In exponential form, y equals e to the x we could do. That's like doing a PERT equation. We have that on our calculator. To do the inverse, we would switch x and y, and we would get x equals e to the y. But we have the same exact problem we've had with the others, and that is you cannot undo that y power with a y root. So it cannot graph in this form. We really need to try to get y equals. And that herein lies the problem of all these. So again, by definition, and that's the only way we're going to get this thing graphed, is we could say let, and put it in log form, if we're looking to graph e to the y equals x, we would have to graph y equals the ln of x. We like to say natural log, or as the Frenchmen say, la naturale. And so that's why the L is in front of the N. But the natural log is for base E only. I cannot repeat that enough. Cannot emphasize that enough. Base E only. So there's no way it can be base 2, no way it can be base 10, base E. So your statement is, if you want to use log form and say base E, it would look like that. If you want to stick with, hey, this ln, I don't have to write that base E. And that's a little easier. Now, the only thing I would recommend is that you can see right on these two examples, when I write it, it sort of looks like 1n. So when you write these in your paper, so if I was going to say the natural log of 7, I might try script or something a little different, italics, so that it definitely stands out and it does not look like 1n. Okay? But we're going to read them the same way. What's the exponent on the number 1 if I'm in base E? So right away the brain has to be saying E to the 0 power equals 1. It's a true statement. Okay, there's the exponential form, and here's the log form. And that's what we were expecting you to write. Over here, the ln of E equals 1. Well, that means, again, ask yourself, the base here is E to the power of 1. And what is E to the first equal? E. So you should be able to transform, just like we have been all chapter, from logarithmic form to exponential, and from exponential to logarithmic. So the graph, you're going to say, is it look any different? Not really. We can still do our combinations of positives, negatives, and zeros. But again, because we know E is not a really nice number, you might want to grab your calculator, because otherwise you're going to have to do some crazy multiplication by hand and just use your e to the x equation. So if we graphed this equation exactly, we'd be making a little table. And we have our e to the x key, or you can just say e to the power. Okay, just make sure you're using one of the two. e to the power of 2. We'll go for first with our combination. And then we will use all 5 points to graph. So find your e to the x again. It's down the left-hand side of your calculator. And we want 2. And we do that, and we get about a 7.389-ish, but it keeps going, of course. And then if we go e to the first, whoops, don't want answer, I just want e. That would be back to the 2.71828-ish. And again, these keep going forever. Anything to 0, e to the 0 power would be a 1. E to the negative 1. Now, yes, that would be 1 over our 2.718-ish, but we better do 1 divided by second answer. And that's going to give us about a 0.36787, and again, fills the screen. And so now all we have left is 1 divided by, we want our e to the negative second. Oops, sorry. It should have been 1 divided by 2. I said 2 point. 1 divided by our 7.389-ish, which is going to give us about a 0.13533, and again, keeps going on. So you can see our numbers, which is exactly what we wanted. When we come over here to graph, if I count by ones, I've got over 2, up 7-ish, 7.3-ish, so a little above. 1, 2.7-ish, 2.7 is almost 3. A 0 and a 1, and negative 1, and 0.36-ish, and then negative 2, and 0.1-ish. So we're seeing exactly what we've been seeing throughout the entire chapter when we graph an exponential growth, and that is low across the x-axis, takes that turn, goes up, and climbs exponentially. Versus if we do that same thing and we want the exponential, we know in writing that would be x equals e to the y. We can't do that. So the question is, what is the inverse equation? And that's what we said was now our natural log form. So in order to graph that, we should get these same points written in the opposite direction. So I would get 7.389-ish, 6, 7, and about 2, and 2.7718-ish, almost 3, and 1, 1 and 0, a 0.366 and a negative 1-ish, and a 0.133-ish and a negative 2, and we're getting that climb along, cross, and there is our exponent. So we know that when we rewrite this, we should be getting our equation of the ln of our number y has to equal, or ln of our number x has to equal y. So when we rewrote this, we would have y equals the ln of x. And that would be the equation we'd be putting in to help us graph. Looks exactly like all the others, but it's just a new equation. So again, you've seen something like this before, and I'm not going to take as much time because these are all the same properties. You have your anything to the 0 power property. You have your e to the n property. You have your power of a power property that you really multiply. Your like bases, add the exponents, and your like bases in division, and you subtract. So when you see those, what are they going to turn into? You got to recognize them. Difference is these are all e's, so that means we're going to have ln's. So when we have our ln's going through the magic egg here, that would turn into the ln of 1 equals 0, which is really e to the 0 equals 1. Two bases that look alike are basically here. The ln of e to the n equals n. That's how I say it, but this is how I read it. The exponent on the number e to the n in base e is what? It's n. Next one, power of a power. I think I can fit that one up there also. The ln of x to the n equals, this is the one where you have the multiplier out front on one side. If you have a power in your natural log, it becomes a multiplier out front of the ln. The last two are rules for multiplying and dividing. These are fairly long. So if I multiply with a single log, I will add with 2. If I add with 2, I will multiply as 1. And same thing with division. If I divide with 1, I will subtract with 2. If I subtract with 2, I will divide with 1. That's what we're going to do. We're going to get lots of practice in those, so here's just a couple. Let's go. On this first one, everything's there. Rewrite me in what we call logarithmic form. So I'm going to say, what's the exponent? And I notice my base is e, so right away I do my ln, and I like my cursive style. The ln, the natural log of the number 20.1 in base e, and I don't have to write the little e down here, is approximately 3. So I read it. The exponent on the number 20.1 equals 3. You could say in base e if you want. So write me in exponent form. Here's something in ln, so you know it's natural, which means immediately you know it's base e. So here we go. We need exponential. I'm looking for that base. E to the power of 5.58ish. Has to equal or approximately be equal to the number that was being assessed, 264. Now I do agree on these base e's, they're a little tougher because you don't know the multiplication tables of e very well. So take your calculator as a check and multiply this out. E to the power of 5.58 had better be that 264. And last but not least, on one like this where you are missing something, read it for meaning. That's going to help the best. And as I read this one for meaning, I'll just pull the pen across as we go. The exponent on the number e to the negative 6 in base e is what? That's my question. So if that helps you, then you need to say e to the what power equals e to the negative 6. And now you're looking at the answer had better be negative 6. That's one of those, duh, it's right there. What's the exponent on this number when it's written in exponent form? Well, it better be the exponent that you can see. So now we've had 3 different types of logarithms. We've had base 10 or common logs. We've had other bases of logs, log, and now we've had the PERT or base e written in logarithmic form, which turns it into something we call a natural log. So bring questions you have, maybe about the 3 or anything you saw here, to class, and we'll discuss it.